Thank you very much for the introduction and also for inviting me to be a speaker in this meeting today. Yes, I will talk about our experiments that we do at Columbia University here in New York that are related to ultracold molecules and metrology and precision measurement. Molecules have been on the frontier of quantum science in the last 5 to 10 years. And they really allow us to go beyond what we can do with atoms in a range of experimental fields. So some examples involve studying fundamental chemical processes, also designing quantum materials and quantum phases and implementing quantum information protocols. And finally, enhancing our ability to detect fundamental physics phenomena. And the first step, of course, is creating an ensemble of molecules at very low temperatures. One way to create ultracold molecules is to assemble them from atoms that are laser cooled down to the microkelvin temperatures by using light or magnetic fields. So today I will talk about very simple molecules, strontium dimers, strontium-2, which we create by first making excited dimers that then spontaneously decay to the electronic ground state of the molecule. And since these photons take away the binding energy, it means that the resulting molecules are still at just a few microkelvin. So our molecules are trapped in a one-dimensional optical lattice, which is simply a standing wave of retroreflected light. This lattice tightly holds the atoms in these bright microtraps, which we call lattice pancakes. And then the molecules are created in the lattice as well, which preserves these microkelvin temperatures. And any probing light that we need to use then propagates along the lattice axis in order to strongly suppress Doppler dephasing. And this setup is used to create strontium molecules by first laser cooling a strontium atomic beam, which if my cursor is not working, you can see at the top of the photo, and then trapping the atoms in an optical lattice and associating them into molecules. So we use at least about a dozen lasers to create, trap, and probe the molecules. And then inside the vacuum chamber in the inset, you can see a cloud of laser cooled atoms that is very easily visible by eye. Our ultra-cold strontium-2 molecules are essentially van der Waals dimers, and they have two key features, I think, to keep in mind, which I will briefly illustrate here by referring to the relevant potentials of this molecule that are shown on the left. So firstly, here there's a ground state potential, which dissociates into a pair of ground state strontium atoms. And also you see the lowest lying pair of potentials that have the threshold at the intercombination line of strontium. And these are called 0U and 1U. And this intercombination or spin flip line corresponds to the singlet S to triplet P transition in the atom. So one important property of the molecules is the presence of very narrow optical transitions that are of the singlet triplet type. And these narrow transitions provide us with a powerful capability for quantum state control. Now, the second important property that I'd like to also point out is the completely spinless molecular ground state, at least for bosonic strontium isotopes. And this relative simplicity of this potential is an advantage for precise metrology and for ab initio calculations. So to illustrate the point about the ground state van der Waals potential, here you see the ab initio calculated potential shown with red points. and the experimental potential, which is derived from traditional spectroscopy, which is shown with the blue line. And that there's a very good agreement at the level of 1%. So this narrow intercombination transition is an incredibly useful tool also for imaging the molecules. And as we discovered, also for studying quantum state resolved photochemistry. So in this case, that the optical transition is from a bound state to a continuum where the molecule is split into fragments. So on the bottom left, here is a photodissociation spectrum where you can see fragments are created above, but not below the dissociation threshold. And the spectrum is very sharp or very narrow because of this long-lived excited continuum. This means that the fragments can be obtained with very little residual heating, in fact, well below a microkelvin. Then the images here on the top right show the side view of these emerging molecular fragments. Now, when we image these exploding molecules instead by looking into the symmetry axis of the trap rather than from the side, we can observe these non-classical angular distributions that show matter-wave interference very clearly, as you can see on these calculated and experimental images. And this type of interference is really a key feature of ultracold reactions. And here are a couple of specific examples of quantum interference effects in ultracold photochemistry. So the strontium molecules are dissociated here into their ground state continuum, such that all the outgoing quantum states are known and their relative phase is known. So in both cases that I'm showing, we are essentially imaging different coherent superpositions of G-wave spherical harmonics. And these result in the 8-fold fragment patterns that you see. So the experimental images in both cases are on the top right of each square. And then the calculated predictions are illustrated all around it in 3 different ways. So the long-lived intercombination threshold also gives rise to a completely new type of super narrow optical transition in the molecules, which is actually absent in atoms. And this is a transition to the state with the same inversion symmetry as the ground state, which is even or G Gerade. The transition mechanism is magnetic dipole, and the strength of this effect is proportional to the bond length of the molecule squared. So this results in 2 families of excited molecular states. One is a super radiant, which are still quite long-lived, about 10 microseconds, but their decay is electric dipole allowed. And then we have subradiant states with lifetimes of order 10 milliseconds or 3 orders of magnitude longer. And these are, of course, distinguished by the internal wave function, whether it's SP plus PS type or SP minus PS type. And the subradiant states are extremely useful for working with molecules that are trapped in an optical lattice. So for example, we can take broad spectra of these states, and because they're so narrow, we can resolve the expected red and blue lattice trap axial sidebands that you can see in addition to the narrow carrier in the center. And these precise measurements of the axial lattice trap frequency allow us to precisely calibrate the trapping environment and also the molecular density. And then zooming in on the carrier and measuring its asymmetrical width directly gives us the temperature of the molecules with a high accuracy. Here are a few of the questions that we address through our research. So we would like to understand if small molecules can contribute to our understanding of fundamental forces. And this includes both new sort of undiscovered physics, but also, so to say, old physics that, like QED, that plays a critical role in high precision measurements and also in our understanding of atomic and molecular structure. So we are exploring whether it's possible to control molecules across a large range of the electromagnetic spectrum, and also how to decouple their internal dynamics from their environment in order to achieve the most precise quantum control. And finally, we're also investigating whether there is possibly a metrological advantage for using molecular versus atomic systems. So in the title, I mentioned clocks. Basically, a clock is a quantum system that can give us a very precise frequency measurement or frequency reference. And a molecular clock that provides a very precise measurements of the vibrational states is an excellent sensor of the interatomic force. So when the positions of the bound states are known with an uncertainty, say below a part per trillion, then the interatomic potential and the binding force that holds the molecule together can be also reconstructed with a similar precision. And a high precision interatomic force sensing can lead to potential discoveries of new physical forces. For example, it may be possible to use molecular clocks to learn about gravity at the ultra short range. So our strontium molecules can be pictured as sort of pairs of atoms that are separated by their bond length, which can vary from about 0.5 to 5 nanometers. And the bond length, of course, is set mostly by electromagnetic interactions between all the electrons and nuclei. Since the nuclei are relatively heavy, Newtonian gravity also contributes and makes a very tiny correction to the bond. Then possible deviations from Newtonian gravity can be parameterized, for example, using the exponential Yukawa term, which here has a magnitude A and a length scale lambda. So from previous experiments that use quasi-classical methods, we know that at the nanometer scale, A is smaller than 10 to the power of 22. So in other words, there could be quite a huge correction to regular gravity, and it wouldn't contradict any experiments that have looked at interactions between spinless masses. And the molecular clock is a fully quantum system that has the potential to go to higher sensitivities. So from the theoretical point of view, the possible fifth force would be a small correction to the electromagnetic interactions. And in the basic Born-Oppenheimer picture, the energy of a bound molecule consists of the electronic, vibrational, and rotational contributions, although we work with rotationless molecules. And the strontium-2 ground state potential is pure singlet sigma, since strontium-88 has no electronic spin or angular momentum. And this well supports roughly 60 bound states. Then the energy corrections beyond the Born-Oppenheimer would include the adiabatic terms. They're proportional to eta, the electron to nucleus mass ratio, and as well as non-adiabatic or eta squared corrections, then various relativistic and QED corrections that depend on both eta and the fine structure constant alpha. And also finite nuclear size corrections that implicitly depend on the nuclear mass. We believe that it should be possible to describe the leading order corrections in a somewhat analytical form with coefficients that can be partially fitted to the data. And in this way, isolating the mass dependence that is a signature of a gravity-like force. So in particular, strontium has 3 spinless isotopes that can form dimers of multiple mass combinations, supporting hundreds of clock transitions. And that would provide really plenty of information on the mass dependence for different ranges of bond length that correspond to the different vibrational states. Okay, so maybe I will miss a little bit more of the theoretical update unless there are specific questions, but on the experimental side, the molecular clock involves a pair of vibrational clock states that each see the same trap depth in a so-called magic optical lattice. By magic, we exactly mean the fact that the two relevant clock states see exactly the same depth. And these clock states are coherently coupled to each other. But since direct transitions are forbidden, we drive a 2-photon clock transition, which off-resonantly couples to a narrow electronically excited molecular state. So here, the ground and excited molecular potentials are shown in more detail so that we can understand the clock scheme better. So the clock states 1 and 2 are vibrational levels in the ground state of the molecule. So here 1 is the most weakly bound and 2 is quite deeply bound. The clock states are coupled by a coherent Raman transition through an off-resonant intermediate state. And then the optical lattice frequency, the frequency of the trap light, is shown with the dashed yellow line. And that's red detuned from that first excited threshold. So we can focus on the relevant quantum states. So in orange and blue are the upper and lower clock states, which here happen to have vibrational numbers 62 and 6 and no rotational angular momentum. And then in addition, the lattice, this yellow line, is near resonance with a transition from clock state 2 to a deeply bound rho vibrational state in the excited 1U potential. And this state is highlighted in green. So when the molecules are sitting in an infrared lattice, the clock states are both downshifted in energy, and therefore the molecules are optically trapped. But generally, the two clock states will see different trap depths. And because of this, the clock transition ends up being light shifted and also broadened due to the thermal spread of the molecules. But when the lattice frequency is deliberately blue detuned slightly from the green intermediate state, then that stark shift pulls the blue and green states slightly closer together. And at a specific lattice frequency, this trap depth that I call U for clock state 2, then exactly matches the trap depth for clock state 1. And this is what we call the magic wavelength, at which the clock resonance is expected to sharply narrow, since it's no longer limited by this inhomogeneous stark broadening. And both states here see exactly the same trap depth. So as we sweep the lattice frequency through the narrow resonance, we can directly measure the stark shift of this deeply bound clock state 2. That's the one that we are controlling by sweeping the lattice frequency. So here in this plot, we change the lattice frequency by about 10 gigahertz around the resonance, and we see the dispersive stark shift curve of clock state 2. And the green bar, the vertical green line, shows the lattice frequency where the polarizabilities and stark shifts of the two clock states are equal to each other, which corresponds to the magic frequency. And this is here that we expect to see the narrowest clock resonance or the longest coherence time of the clock state superposition. One way to search for these magic wavelengths is to measure the clock shift versus the trapping light power at different wavelengths, which are shown here in different colors. So the wavelength with a 0 slope is magic, and here this is the red line. Yes, so and here corresponding to each lattice frequency, we also plot the clock resonance line width for each value of the lattice frequency. And you can see that the baseline width is quite large because of this lattice-induced broadening. And then as you go from left to right on this second plot, the line width increases even further as we approach the resonance. But at the magic frequency value here on the blue side of the resonance, it dramatically drops by over 3 orders of magnitude. So here are a couple of the clock spectra on either side of the resonance, but away from the magic frequency. And we do see the expected light shifts and light-induced broadening from the lattice light, both on the order of about 100 kilohertz. But at the magic frequency, the resonance is symmetric and very narrow. So here is the zoomed in spectrum of the vibrational clock resonance at a magic lattice frequency. This resonance is 30 hertz wide, which is about a 3,000-fold improvement over a non-magic lattice wavelength. So the resonance frequency for this clock state pair is 25 terahertz. So this spectrum corresponds to the quality factor of 8 times 10 to the 11. And as a side note, I'll say that the Blackbody radiation limited intrinsic quality factor of this clock is extremely large, here many orders of magnitude bigger. So in practice, we will be limited by our technical finesse. Okay, so besides just using the narrow width of the clock resonance to quantify the coherence of the clock states in the magic lattice, we can instead directly drive quantum Rabi oscillations between the clock states. So in this case, the molecule is made to oscillate between its tightly bound state and its weakly bound state that has a long kind of floppy bond. And a well-chosen magic frequency helps us reach a very long coherence times for the molecular clock. So here is the quantum Rabi oscillation between the molecules in vibrational states that are separated by almost 30 terahertz. And this oscillation decays with a long time constant of approximately 130 milliseconds. So here we are not yet limited by the just 2-body collisional lifetime of the molecules, which you can see here. It's shown with purple triangles for the upper clock state. So we're not quite there yet, but instead we're currently limited by the lattice-induced loss of molecules in the lowest clock state, which is the state that does talk to the optical lattice. And this is shown with the red squares. And so here is a somewhat more careful look at the lifetime of the deeply bound clock state 2, the one that whose trap depth gets tuned by the lattice. So away from the magic lattice frequency, it shows a typical 2-body decay. This is the green curve, where more than half of the molecules are still remaining after, say, 100 milliseconds. But at the magic wavelength, which also happens to be quite close to a lattice-induced resonance, this is this pink trace, the molecule loss is much more severe, and here almost no molecules are left by 100 milliseconds. Now this magic lattice loss is exponential rather than 2-body, potentially indicating that there is lattice light scattering. And from our knowledge of the lattice-driven transition, from ab initio calculations that are supported by some of our measurements, we are not expecting to see such fast loss, and we are investigating the possible reasons for it. But still, we do have control over the choice of a magic wavelength out of really multiple options that are fortunately available in molecules, and we can choose ones that cause the least unwanted light scattering. So for example, we can use this type of plot to help us choose optimal magic wavelengths. Here we use colors to show the coupling strengths or transition dipole moments squared between the strontium-2 ground state vibrational levels on the vertical axis and the 1U, these intermediate excited states on the horizontal axis. And the brighter colors indicate stronger coupling. So we see a fairly typical pattern that arises because the molecule spends the most time in its sort of inner and outer turning points, which gives rise to the two branches. So since we are interested in at least one deeply bound clock state, here I zoom in on the lower left corner. And so this shows coupling strength for the lowest 10 vibrational states. Near this bottom of the potential, the energy structure is fairly harmonic. And this harmonicity shows up in this distinctive checkerboard pattern of low and high transition strength. So our first experiment used the state pair highlighted with the white rectangle, which is relatively strong, but doesn't lie in one of the bright branches. Then we went on to use this state pair with the black rectangle, and this did lead to longer Rabi oscillations, in fact, the ones that I showed you today. And more recently, we found a magic wavelength with an even larger magic detuning corresponding to a stronger lattice-driven transition, which corresponds here to the red rectangle. This is actually the largest transition strength that we expect for this molecule. And this involves the absolute ground state as one of our clock states. Just as a very small detour, when we're not at the magic wavelength, when the molecules are just sitting in the lattice, we experience sort of expected two-body loss that is not light-driven, but arises because the molecules are still free to collide in these lattice pancakes. And the collisional loss of the ultra-cold strontium-2 molecules is somewhat interesting in itself. So this non-polar van der Waals dimer is quite a new type of molecule for ultra-cold collision studies. The formation of alkaline earth trimers, in this case, this would be strontium-3, is favorable and releases a lot of energy. So reaction rates could be expected to be close to the so-called universal limit. And in this universal regime, reaction rates are mostly independent of the molecule's vibrational state. Now, because of the short reactive lifetime, we don't know currently whether the intermediate strontium-4 complex get rapidly excited by the trap light or not, as is the case for some alkali metal dimers. But in the future, in order to avoid collisions altogether and to increase the molecular lifetimes, the molecules can be trapped in a three-dimensional optical lattice where each particle is separated and is by itself. And here's a careful measurement of the two-body collisional loss over time. So you can see that one-body exponential loss, which is the blue dashed line, really does not describe the story, but a two-body loss, which is the red line, fits the data very well out to long times. And moreover, at the long times, we end up with roughly half a molecule per lattice site, which makes sense to us because that corresponds to sort of complete loss in the lattice sites with an even initial number of molecules and then one molecule remaining in the sites that had an odd number. So the average is 1/2. Then in the inset are the measured two-body loss rates for our molecules in the most deeply bound state and in the least bound vibrational states. And the loss of the deeply bound molecules agrees very well with the universal rate prediction at 6 microkelvin, which is the dotted line. while the loss of the weakly bound dimers, which have more structural complexity, is larger by about a factor of 2. So here, I of course mentioned our studies of molecular collisions in the absolute ground state of the molecule, but I haven't yet shown you how these how we can create these deeply bound molecules in the experiment. So initially, the molecules that we make from laser cooled atoms are weakly bound. They're in one of the highest vibrational states. But now we can also create samples of ground state strontium-2, which is the first ultracold molecule of this type. So to do this, we momentarily switch off the lattice, and this removes decoherence from the light shifts and results in very narrow EIT signals like the one shown here. This is electromagnetically induced transparency, where the pump and probe coherently connect the highest and lowest states in the molecular potential. And in this free space environment, we implement STIRAP, or stimulated Raman adiabatic passage. So initially, all our molecules are in the weakly bound state, which we call V-1. Then the resonant Raman lasers are smoothly pulsed on and off to transfer the molecules to the ground state, which is V0. We can't see these deeply bound molecules directly, so they look dark. But after we reverse the STIRAP process, we can recover the molecules again in the weakly bound state, V-1. And from the number of the recovered molecules, we deduce the one-way transfer efficiency, which is currently up to 90%. And the black line here is a simulation based on optical block equations. Okay. I think I can't see the chat, but how is the time? Probably.
Yeah, basically we should
go to questions. Okay, that's fine. So I'll skip a little bit about some more discussion of other types of magic wavelengths and how this relates to potentially black-body radiation shifts. Yeah, I'll just say that we have already done a preliminary scan of all the clock states, at least in the dominant isotope, strontium-88 dimer. And now we are working on increasing precision to the metrological level. So just a brief summary, we've created samples of ultracold van der Waals molecules in the absolute ground state. We have very good control of their quantum states. And we use the molecules to demonstrate a vibrational molecular lattice clock, which achieves about a quality factor of 1 trillion, 10 to the 12, and coherence time of 100 milliseconds across the entire molecular potential. Actually, this clock we first proposed some years ago for measuring slow time variations of the electron to proton mass ratio. But we are also excited about its applications for sort of these sub-part per trillion interatomic force measurements and potential searches for new mass-dependent forces. So to conclude, I would like to thank my graduate students who worked very hard on the experiment. And also we thank our theory colleagues, actually from Warsaw, Robert and Ivana, who help us with ab initio calculations for strontium-2. And thank you for your attention.
Yeah, many thanks, Tanya, for a great talk. Do we have questions in the audience? Maybe I give the audience some time and start myself with a question, Tanya. Tanya, you interrogate your clock with a 2-photon Raman type clock laser, right? So I wonder, don't you have problems with light shifts from your 2 lasers, or do you have to do some? To what level do you have to stabilize them in power?
Right. So yeah, that's the one concerning systematic effect compared to 1-photon clocks, is because the 2 photons are both kind of off resonant some transitions, you get stark shifts due to both, and they have to be controlled. So to the lowest order, we control that stark shift by balancing the intensity ratio of the two Raman photons. So if you balance their intensities such that the Rabi rates are essentially the same, and you work with us, so you can be with the red detuning or blue detuning relative to the intermediate state, and in one of those choices, the stark shifts due to the two lasers go in opposite directions, and then you can choose this kind of magic ratio, intensity ratio, where you cancel the stark shift. So that's what we do for now, and we can do better by just technically improving the stability to, but it's difficult to improve stability to beyond, say, 1% or something, maybe a little bit better than that. So we might need to go to some more complicated schemes to suppress this effect further. But for now, we just use the magic intensity ratio.
Okay, thanks. Mm-hmm. Questions? I mean, I have a bunch of, but maybe I just go on, Tanya, if no one asks. So, go ahead. So I was wondering, the other thing I was wondering, when dealing with Rydberg atoms, we always have problems with Blackbody radiation coupling nearby states, right? So you also have in the molecules a lot of nearby states. So I was wondering, are all those transitions really forbidden on the single and also on the 2-photon level probably? Because of, I guess you care on that level. Yeah. So when on one of the slides, I put down the sort of the natural quality factor is something ridiculously high, like 10 to the 26. That includes Blackbody excitation. It's just extremely inefficient because here, these are non-polar molecules. So the direct vibrational transitions are not allowed. And then because of the this quantum symmetry, that it's a boson, two identical bosons, right? You can't have, for example, you cannot have odd rotational states in the ground state of the molecule. They just don't exist. And so the transition from even to even rotational states are also very highly forbidden. And Robert's student Ivana, who's here on the slide, she calculated all the contributions and came up with very, very tiny numbers. So like 10 to the 5 years of natural lifetime or something like that. So it's the other thing. So besides the lifetime, of course, you have to worry about shift, just right, clock shifts from Blackbody radiation. And so I skipped that slide a little bit, but it seems like there are choices of clock transitions where the two states are where the Blackbody wavelength, which is about 10 microns roughly, is kind of quasi-magic for those clock state pairs, which means if you choose those pairs, then you have very low shift due to Blackbody radiation. So that we haven't proven experimentally, but that's the expectation. Okay, thank you, Tanya. Any question in the audience? Otherwise, I would say chat. No, nothing in the chat. So, well, then, Tanya, thanks again for your great talk.